Yesterday we talked about Arrhenius' definition of acids and bases, and you will be handing this lab in to me here probably tomorrow, yes? About acids and bases, Arrhenius definition. Yesterday we looked at his definition, and his definition said the following here, if you remember from yesterday, right down here at the bottom. It says that Arrhenius acid is a substance that ionizes to form hydrogen ions. Okay? So basically we said, hey, you know what? It needs to form those ions when you put it into water. It needs to ionize into H+ ions. And an Arrhenius base is anything that dissociates, okay, to form hydroxide ions in that case there. Okay? And so then we asked you to predict those. We went to the lab. One of the questions there is, does any surprise you? Which ones, is there any that surprised you yesterday? Which ones surprised you from yesterday? Or which ones didn't quite work out the way you thought they were gonna? Anyone? Yeah, Cole? CH3COOH? Sure, that's one that can be a little confusing for sure, yeah. Okay, what else? Any other ones? Any other ones? What's another one? There's at least another one for sure. Sometimes two, maybe even more in some cases. Depends on your knowledge of compounds, basically. What else is another one? Yeah, it is neutral, yeah. That one's a little bit maybe surprising too, because you do have some hydrogens in there. You do have some oxygens. Is there a chance that there's some OH in there? Possibly. We don't really know what that structure looks like, so possibly, yeah. Is there any other ones that kind of surprised you a little? There's probably one other one for sure. Which one? Any other one? No? You guessed them all? What's the other one? Huh? Yeah. Close to the bottom there. That one's definitely surprising, yep. And there's probably another one too. Yep. Yep. Yeah, that one I don't know. That one shouldn't be surprising, but that one turned out to be an acid, I think, for some reason. I don't know why. I'm not sure why. That really should be just ionic compound neutral. Should be. Maybe it's just like maybe they're a little bit got in there. I don't know. But yeah, it's a little bit. Yeah, NH3, right? I mean, look at this definition right here from yesterday. Who would have predicted that NH3 was a base? Okay, probably based on this definition, probably not many. Yeah, look, it says here an Arrhenius base is a substance that dissociates to form hydroxide. Do you even see hydroxide in NH3? There's no O there. Okay, yeah, there's a couple H's, but there's no O's. So, you know, that doesn't really make sense, does it? And this is what Arrhenius came up with. This is actually the same thing. He's like, well, geez, that doesn't work. So he said, I got to fix it. So he fixed it. And instead of calling it the Arrhenius theory, he said, you know what? There's nothing wrong with these definitions. They do work. Because look at, you remember the sodium hydroxide one? It's got hydroxide, yeah? So it dissociates to form hydroxide. That's good, right? So there's nothing wrong with these definitions, but it doesn't encompass all the possibilities. So he said, you know what? I got to modify my definition. So instead of coming up with like a totally new name for it, he said, hey, let's call it the modified Arrhenius theory. Huh, that's smart, eh? So that's what he did. He said, you know, after we test all these solutions like we did in the lab yesterday, he said, they don't work for all of them. Those definitions don't work. I need to adjust it somehow. So before we get to his adjusted definitions, we are going to talk about, which by the way are down here. I guess we could probably talk about them now. The acid one's probably not going to make a lot of sense to you right now until we go back and do this. But he said an Arrhenius acid reacts with water to produce H3O+ ions. That's his new definition of an acid. And his new definition of a base still has that old definition of a base. Look, an Arrhenius base dissociates to produce hydroxide ions. Isn't that what we just had on the last lesson that I showed you? Sure it is. okay? But he also said, hey, an Arrhenius base can also react with water to produce hydroxide, okay? So when you think about NH3, that doesn't have hydroxide built into it, but it can react with water to produce hydroxide, okay? Because these substances were all put into water yesterday, okay? So that's what we're going to talk about a little bit today here, all right? Let's go back to here for a second. The first thing we're going to talk about is the acid part here, the hydronium ion. You should know this hydronium ion thing here. I'm going to draw it for you, et cetera, and I'll show you how it forms. It does turn out that recent discoveries, as when we say recent, we mean 1900, okay? Basically, discoveries have shown that there is no such thing. When you put hydrogen chloride gas into water and it ionizes, so this is what we've been writing so far, right? Don't worry about this part here. This is what we've been writing so far, yes? We would say that with an acid, yes? Do you agree? Okay. That was his definition yesterday. That's his Arrhenius definition. When you put HCl into water, it ionizes and it gives you H plus ions and Cl minus ions. After much research, turns out they did this and then they looked for the hydrogen ions. Okay, they got their little microscopes out and did all their little fancy little tests and whatnot. Not microscopes. You still can't see it. But anyway, that was kind of supposed to be a joke, but no one laughed, so that's fine. We'll move on. They did analyze the solution, and it turns out they can't find any H plus ions in the solution. There is no such thing as this by themselves in water. When you put an acid into water, they couldn't find any H plus. Turns out, all you can find is what we call this hydronium ion right here, okay? And how that works is this, basically. Water, we know, is polar. Yes? As in bear, right? That has nothing to do with this, but I just figured polar bear kind of goes. I read a lot of National Geographic right now with my son, so polar bears. Did you know their fur's hollow and their skin's black? You knew that, right? You learn a lot from well, not grade 3, 3- and 4-year-old magazines. Their hair is hollow, it's actually clear, and it conducts the sun's light, and their skin's black. Yeah, which has nothing to do with this. Okay, I'm just saying, if you're looking for some information, National Geographic little kids. Don't get the other one. Don't get kids. I don't know. We should probably stop this. Don't get kids because there's a lot of advertising in there. You need the little kids. And you can find the differences too, you know, between the two animals. It's fun. Okay? So we got water here, right? Water's polar. So it's got a negative end and a positive end to it, yes? And then we dump some acid into here, and the acid, of course, has H plus ions, hydrogen ions, right? Well, the hydrogen ions just don't float around by themselves. They, like I said, they looked for them. They couldn't find them. There's none floating around by themselves. Turns out that the hydrogen ions, I don't know why I wrote that other one down there, attach themselves to the water, okay? Because water's polar, it's got a negative end, and that ion is positive, it's attracted, and they actually make a new ion there called the hydronium ion. That you can find in water. That you can find a lot of. Okay, it is basically an H plus added onto a water molecule. They combine together. So what we know now is that we had to, when he said his modified definition makes that all acids make hydronium ions, that was a modification that he made because he looked for the hydrogen ions, we couldn't find any. Turns out that they add themselves onto water. We've done this before, guys. H3O plus, hey, 3 electrons, 6 electrons. Oh, plus 1 means we've lost 1, yes? We could draw this, right? We've done this before. O goes in the middle. We're drawing a polyatomic ion. H, H, H. 1, 2, 3, 4, 5, 6, 7, 8. That's your new hydronium ion. Okay? We get away with that. Basically, you might say, well, how does that work? Well, think of water. How many lone pairs does water have? How many lone pairs does water have? Look there. How many lone pairs? Cool? 2, right? Hydrogen has 1 electron, but it's been given off, yes? Yeah? Because it's an H plus now. So the electron's gone. One of these lone pairs is acting as a bonding pair now, okay? To get that hydrogen into there now, right? That 1 electron's been gone now. So that's how you get the hydronium ion. That's what's responsible for acidic properties. So yesterday when you guys measured pH, and with the pH, well, you guys didn't do the pH meter yesterday, but pH paper, you're measuring hydronium ions, how many there are in there. Okay, and we're going to talk a little bit more about that at the end of today here. Okay? So, an Arrhenius acid reacts with water to produce hydronium. Here's an example. Okay? We're just going to focus on the acid for right now. So when you look at this example here, this would be the new definition. So yesterday we would say HCl gives you H plus and Cl minus. Today we would say HCl plus water gives you H3O plus and Cl minus. And here's how it works, so pay attention. HCl is really made up of these 2 ions that have joined together, yes? Okay? Hydrogen chloride. When you put it into water, it does ionize into H plus ions and Cl minus ions. The H plus ions attaches itself to the water. So think about that. H plus added onto water is H3O plus. So this attaches itself onto this and makes that. Okay? H plus is added onto the H2O to give you H3O plus. Okay, the hydronium ion. What's left over? The only thing that's left is this right here, which is your negative ion. Okay? All acids behave like that. And we're going to do lots of examples here coming up today. But that's what's happening. That's what actually happens. This is called the modified Arrhenius definition of an acid. And this is what truly happens when you put acid into water. It reacts with the water to form the hydronium ion. Any questions? Yes? It's not all wrong, okay? In fact, it's quite often, they're both acceptable to write. So when we get to the actual equations for figuring out pH and things like that, we actually have 2 ways we do it. And it just depends on what you want to do. What we're trying to tell you is this. There's nothing wrong, and we'll do it in Chem 30, and you'll probably do it in university with hydrogen ions. So going back to this here, what I wrote right here. Okay, you'll still use that, and you can still use that. It's fine. But what we need you to understand is also this, that technically, when we say that, you have to understand that that H plus is not by itself. It is attached with a water. So is this correct? The answer is yes. Is it the best explanation? The answer is no. The best explanation is this here, okay, the modified Arrhenius theory. All right. So the answer is, what do you want to see later on? Well, I want to see kind of both. I want you to know the difference between the first definition and the second definition and how things have changed since yesterday to today kind of thing. I want you to understand that this is probably a better definition of what's really happening. Okay? We're going to talk about the bases now, and the bases are a little bit more tricky because all acids look like that. All of them look like that. Acid plus water gives you a hydronium plus the negative part. Okay, all of them do. You could set up a spreadsheet or whatever, and you could just fill this in as you go along. They all do exactly the same thing. However, the bases are trickier because the bases have 2 parts to their definition. First, it says, if it's got hydroxide in the formula, look, barium hydroxide, I'll do another one here, sodium hydroxide. If you put that into water, you'll get sodium ions and hydroxide ions. That is known as Arrhenius' definition of a base. It's also exactly the same for his modified definition. Both of those were the same. Remember how I underlined dissociates in water? Dissociates in water? They're both the same. So if I said, show me the Arrhenius definition of sodium hydroxide, you could give me this. If I said, what's the modified definition of sodium hydroxide, you'd say this. Same. Because it's already got hydroxide built into it, and it simply dissociates to give you hydroxide. So this is both the Arrhenius theory and the modified Arrhenius theory. No difference. Okay? Because yesterday we said it had to dissociate to give you hydroxide. We said that today as well. It can dissociate to give you hydroxide. What we didn't do yesterday was what happens when you get NH3, for example. Can that just simply dissociate? Can that just break apart and give you hydroxide there? Look at that compound. Can that just break apart and give you hydroxide? No, there's no hydroxide there. So in this case, his modified definition, yesterday we said, well, I don't know what to do with that. Yesterday, it doesn't dissociate to give you hydroxide, so I guess it's not a base. Yesterday. Today, we'd say, okay, it can dissociate or react with water to give you a base. Okay? So, what is that going to look like? Well, all bases, this is not untrue. He said yesterday all bases have to have hydroxide. Today we're saying the same thing. They always have to produce hydroxide. Same thing. So, now we need to talk a little bit about some other things here as well. Okay? So, first things first. Okay, NH3 is a molecular compound. Okay? Turns out it is a base, yes, but it needs to react with water in order to produce that hydroxide. So when I made this yesterday, I took the ammonia and I dumped it in some water to give you some hydroxide, and that's basically how I made this. Okay. Having said that, okay, we have to understand how am I going to get hydroxide here, and this kind of is going to go into what we're going to talk about today with pH and POH and H plus ions and OH minus ions. Water. Let me ask you this question. Is water an acid? Is it a base or is it neutral? Which one do you think? Yes. Water is generally neutral. Okay? However, water is also made up of H's and OH's. Okay? At times, water is made up of those two ions. Okay? Water can partially ionize. Okay? If you think about strong and weak acids that we've talked about in lesson 1, remember the strong acids always completely break apart into ions, yes? HCl, H plus, Cl minus. Yeah? Weak acids. How many actually break up for weak acids? Do you remember? Out of 100, how many break up for a weak acid? Well, sure. Not many. Okay? Well, what's water? It's actually kind of like a weak acid, weak base. Or you could say, in some cases, maybe a strong acid, strong base. But water is made up of H plus and OH minus sometimes. The good news about that is, first of all, when you drink water, if you drank 1,000 molecules of water, how many would be HOH, like the molecular compound? Well, most of them would be HOH, right? Most of them would look like this. Yes? Molecular compound neutral. In that water, out of 1,000, would you possibly find one H plus and one OH minus? And the answer is yes, you will. Water can partially ionize, turn into ionize, molecular compound turning into an acid. Yes? But look, what is water made up of? H plus and OH minus. So not only is it an acid, not only do for every acid you also have a base. So does that make it neutral still? Sure it does. So you might drink some ionized water, H plus and OH minus, but you would never tell the difference because it's acid and base which cancel each other out anyway. And for every acid you have an equal base. And it has to work out that way because every water molecule, if you're going to break it up, you're going to get one hydrogen and you're going to get one OH. Okay, that's what comes out of water. You're not going to get many of them, I'll tell you right now. Out of 1,000, you're going to get 999 like this, but you will get a couple like this. And when this happens, and it does, okay, look, here's your base, right? So I'm going to NH3 plus this. That's your base there. This needs to get added on to that, though. Okay? So instead of NH3, we actually get what's called NH4, which is the ammonium ion. Okay? And that's how this particular one, which is a special one, I want you to know this one. Ammonia is a special one. We will spend a little bit, we do probably most of our work with ammonia if we're going to do anything. This is a particular one and a special one, but it creates the ammonium ion and the hydroxide ion. Do you think, now in order for this to happen, listen, in order for this to happen, you have to find the H plus and the OH minus in water. How many are there in water? Lots or not many?
Not many.
Not many is the correct answer. Told you. Good thing you showed up and didn't do plyometrics today. You're valuable here, right? So, yeah, there's not many. So how many of these are you going to get? Lots or not many? Yeah, not many, okay? And since you don't get many of those, guess what? We're going to put a double arrow here to represent that this is a weak reaction. It's a weak base, okay? And we're going to talk about weak bases today and strong bases and strong acids and weak acids and all that stuff. But this is actually turns out to be a pretty weak base. Now, I don't know what you guys measured for this base yesterday. For NH3, what did you guys get for pH on that? 11? Anybody else different? It's okay. Anything else? 10? 12? Okay. Now 10, 11, 12, not fairly strong base, right? So what did I do? Well, probably got a little bit happy with the NH3, as Phil would say, happy, 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 yeah. And got a little happy with the NH3 and dumped it probably a little bit more in than I should have, yeah. But all things being equal, what would you get for conductivity on that one? NH3. 2? Okay. 8? Okay. What else? Huh? 7? Okay. What did you get for conductivity on the sodium hydroxide one? NaOH. 9? 8? Okay. Now, sodium hydroxide, we'll learn the difference here, is a strong base. So technically, usually higher pHs, better conductivity because it breaks up better. Okay? Weak bases tend to not break up very well, and therefore conductivity usually a little bit lower. Now, obviously, I put way too much in because it should have been lower than that, all things being equal. Okay? But I probably put a little too much in. So, we'll talk about this in a second here, but like I said, not all bases have OH minus as part of their chemical formula. If that's the case, we need to react it with water to give you hydroxide. Okay? There is two things you need to know about this, and this is going to get a little bit confusing as well. However, when you start reacting things with water, there's always a chance you could form an acid or a base. Okay? Now, non-metal oxides. So look here. We need to write this down. Non-metallic oxides will form acids when placed into water. Okay. Non-metallic oxides will form acids when placed into water. I'm going to leave a little bit of room here. Leave a little bit. Actually, I'll give you some examples first. Let's do that maybe first. We'll take care of this. Non-metallic oxides, non-metal oxides. So there's already one up there, CO2, for example, is a non-metal. Carbon is a non-metal oxide. Let's do SO2 is a non-metal oxide. SO3, same thing, non-metal oxide. Okay, and there's other ones as well. When those are placed into water, they can or tend to form acids. Okay, when you think, for example, of non-metal oxides, you think, well, here's an example here, carbon dioxide gas. Remember, we don't hear about, we don't really talk about this anymore, do we? Acid rain? Do we ever talk about that anymore? Not really, right? So all the pollution that we were putting into the environment, carbon dioxide gases, right? When those travel up, when CO2 travels up into the atmosphere, is there a chance it's going to react with water? Sure it is. There's moisture in the water, there's moisture in the air all the time, okay? If it rains, there's going to be moisture in the air. So when the carbon dioxide gas touches the water, it forms the beginning of an acid. And I'm going to show you how that does that. When that breaks apart, you get hydronium ions, you get acid, okay? So it is a two-step process. It is a fairly weak acid, which we'll learn today, but still can have a huge effect on our environment, right? So we need to cut that carbon dioxide pollution and all those other pollutions out because they can form acids in some cases, all right? Metallic oxides will form bases when placed in water. Okay. Metallic oxides. Metallic oxides, we think about metal oxides. Metal oxides, well, there's lots of them. Barium oxide is an example of a metal oxide. When you place that into water, you will get a base. Okay. It will undergo what we call a two-step reaction, which I will show you on the next page here. It will undergo a two-step reaction and it will form hydroxide. Okay. Sodium oxide will form a base. Okay. Any basically metal oxide has that potential to form a base. Okay. Now we're going to take a look at some 4 examples here. They are a little bit much, maybe perhaps, but we want you to understand what's going on here. Okay. I'm probably not going to ask you any of these questions on a test or the final or anything like that, so don't freak out, but we do want you to understand how these things can become acids or how they can become bases. All right? So for example, CO2 is the first one I just talked about. When CO2 reacts with water, okay, if you add all that stuff together, look up here, CO2 and H2O, add it all together, what do you get? H2CO3 right there, right? H2CO3, that is called hydrogen carbonate, right? It's got hydrogen in it now. It's a molecular compound, hydrogen carbonate, and it has the potential, if it reacts with water, to form acid, okay? Is there going to be any other water around after it forms H2CO3? Probably, right? If it's raining out and you're pumping CO2 gas into the air, there's always going to be some extra water molecules hanging around looking to make an acid, okay? So we take this now is newly formed, and we're going to react that with more water, okay? Or you could even just do this in the lab. You could take some CO2 gas and put it into water, okay? The first thing you would get is H2CO3. It would combine together and make this new compound. The second thing that would happen is that H2CO3 would break up, react with more water, break up, and form this and this. And it does that by the following. Hydrogen carbonate is made up of that, correct? Hydrogen's a 1 plus, carbonate's a 2 minus, swap and drop, yes? Each hydrogen's a 1 plus, I need 2 of those to go with 1 carbonate, yes? True? Okay. By the way, when an acid has more than 1 hydrogen ion like this, we call that a polyprotic acid. It means that it has more than 1 hydrogen ion that it can donate or basically make an acid from. Okay? We're going to talk about that today as well. So that's called a polyprotic acid. Okay? So, look, what do you have here? How does this equation work? And the answer is it works like this. Just like before. An acid reacts with water to give you hydronium ions and whatever's left over. So here's your acid. This is going to attach itself to this to make that. Okay? True? All acids do that. Guaranteed. Okay? Whether it's strong or weak or whatever, doesn't matter. Any acid you ever have does that. The H plus will attach itself to the water and become H3O plus ions, hydronium ions. What's left over? Well, this is what's left over. If you look at that combined together, H is a 1 plus, CO3 is a 2 minus. If I combine that together, what do you get as an overall charge? You get H, CO3, 2 minus 1 plus, overall, minus 1. Yes? So that is what is left over here. Okay? Now, a couple things happen also here. It's not going to happen with this one. Okay? But I will tell you this. Okay? I'm going to tell you, this is a weak acid. Okay? I know that because, well, because I kind of know what's coming up in the next lesson, which I know you don't know yet. And 2, always a key to look at. Look, double arrow right here, double arrow right here. The double arrow tells you that it's weak. Not all of the initial stuff is turning into the products. It is what we call equilibrium. It goes back and forth, back and forth. Okay? So this is an example of a weak acid or a weak base when you see the double arrows. Okay? Look, remember, this was made up of a 1 plus and a 2 minus here for these 2 ions here, remember? And we combine them together. Is there another H plus that could react with water again to form another acid? So could I take HCO3 minus, is that got an H plus built into it? It does. React it with water to form another acid here, for example? And the answer is technically there is there. Okay? So this could keep going until you run out of H pluses. So it might occur once, it might occur twice, and it might even occur, in some cases, 3 times. Okay? But I will tell you right now, just so you know, that this is very, very, very unlikely to happen. Because once you get to a certain point, even if you had a strong acid to start with, the most you ever get is probably 2 equations out of that. So there's only 2 acids that are technically could be produced from that. The first one, absolutely. The second one, maybe, but very small. The third one is so small and insignificant that it probably doesn't even have enough strength to actually go through with that. Okay? So that is a possibility in some cases, but probably, well, never with a weak acid. Okay? Strong acids maybe will do that twice, and I'll show you an example of that coming up. But a weak acid, you'll be lucky if you get it to ionize once. And even after it ionizes once, how many of these do you think you have in a weak acid? Not many. Okay? And this is a weak acid. Couple clues. Well, next lesson and double arrow. Okay. Here's another example of an acid here. Okay, SO2. SO2 and this combine together. So add those two together and you get this all together. That, once again, is made up of H+, and SO3 2 minus. As always, how are acids formed? H+ adds itself onto the water to make that. Okay? What's left over? Well, whatever's left over, right? That is that. Okay? Once again, you can see double arrows here, so we know that this is a weak acid. Goes both ways. Okay? How many actual H3O plus ions are you going to get out of this here? Not many. Okay? Not many at all. Okay? Yep. Which ones? Well, this one here attaches itself to the water to make H3O plus. The leftover one combines with this here to give you that new ion. Okay? It has to, well, basically you can think of it this way. If this is a 1 plus, altogether this has to be a 1 minus, right? Because we still need to account for those charges. So if that one's giving off its electron, where is that electron going? It's going to the other part that's left over. This H plus right here is actually this one right here. That's the 1 plus right there. And that's the 2 minus, the SO3 2 minus. But when you combine them together, the overall charge on all that is a 1 minus. Okay? Those are what acids do. Okay? And once again, if you notice, these start with non-metallic oxides. So non-metallic oxides will form acids. The metal oxides, which we're going to spend less time on here, will form bases. Okay? And you just have to kind of look at this and say, hey, if I start with a metal oxide, I need to know that it's going to give me hydroxide at some point. Look, this and this combined together will give you all of this. Okay, and you might have to do a little stretch for that, but look, there's 2 NAs, there's 2 O's, and there's 2 hydrogens. If you combine all that together, and you know that it's a metal metal oxide that forms into a metal hydroxide is how that works. All of them do that. You'll see that there's a sodium hydroxide there. That can simply break apart now. So this is kind of Arrhenius, modified Arrhenius definition part 2. Just breaks apart and gives you hydroxide. That's an example of a strong base. You'll see all single arrows there because that's a strong base example. Same with this one here, barium oxide, metal oxide with water. Add all this stuff together. What do you got? 1 barium, 2 oxygens, 2 hydrogens. You know you have to make a hydroxide, so think about the formula, barium hydroxide, 2 plus, 1 minus. You get that formula there. That breaks apart into these 2 here. Okay? We'll talk about the sodium oxide and the barium oxide right away here. Okay? That's pretty much what you need to know from that there. Okay? Which is a lot of stuff, I realize.